Hello everyone, I'm M. Saqib Hossain. I'll be explaining all the questions. So for the first question, we have given an AVL tree storing numeric values. Design an algorithm to efficiently return the sum of all values within a given range L, R. And the follow-up question is, how would your approach scale if each tree update must propagate feature for downstream ML models? Now we need to understand what is a AVL tree. So our AVL tree is basically a self-balancing binary search tree. uh, it actually try to balance all the nodes in this tree structure. For every node, all the keys that are in the left subtree must be less than its key, and all the key that are in the right subtree will be always greater than its key. And also it maintains a balance factor. Now this balance factor is basically we basically the height of the left subtree subtract from the height of the right subtree. Now our balance factor always need to be between -1 to +1. If any of the node, we every time we insert or delete or do any kind of operation, it every time it calculates this balance factor. If it remains between these three numbers, it is okay. Or if it doesn't in this range, we actually do the left rotate, right rotate, and make it balanced. Now for this balancing reason, actually the height always remains in logarithmic. If what is actually the height? So height is the length of the longest path from the root to the tree of any leaf node. If the tree is unbalanced, it will be like a linked list. Then the height h can be equal to the number of nodes. So we can say the height will be O of n. But in the AVL tree, as it guarantees that it never grows in a linear structure, doubling the number of nodes can add only one level to the tree. So it maintains a log n relationship with the height. So traversing through all the nodes will cost you big O of log n. Now that we understand that our AVL tree always remains in the log n relationship with the height, now we come to the now we come to the part where we want to efficiently return the sum of all values. Now for this, we actually use a augmented AVL tree. Now what are you augmenting? Actually we are augmenting the subtree sum. Now this subtree sum is the sum of all the keys of all nodes in the subtree. How are we calculating the subtree sum? uh, Subtree sum is calculated basically, we follow this equation where we add the key value and the sum of the left child subtree and sum of the right child subtree, we get the subtree sum. Now as this equation needs only O of 1, it means that we need only constant time to calculate the subtree sum, and we store this subtree sum in every AVL node. We don't need to calculate it every time. So I have actually discussed how this actually efficient, as it is doing it O of 1 rather than complex relationship of O of log n. Now we need to query the range sum query from a given range L, R. Now for this, we will be using the difference of prefix sum concept. Now what is this difference of prefix sum? Let me give you a visual. Yeah, so here we are calculating the prefix sum. Now what is this prefix sum? Let me give a short overview. We need to, like, this is a array and we need to calculate between 2 and 6. So what are we doing? We are taking another array where this array actually is calculating every every block of and adding it the previous block. So here it is 6, next it will be 6 plus 3 9, next it will be 9 minus 2 7. So we're doing this for the all 6 arrays, all 6 value. Now if if we need to calculate from I to Z, suppose here 2 to 6, so what are we doing? We're first calculating from 0 to 6, and then we are subtract it from 0 to 1. So basically the whole equation comes to here. If we are given a range from 2 to 6, we will just give that a of 6 and then negative it from the lower range and -1. So now again, yes, so here I actually have written that equation. So what is this equation? This equation is we need to calculate sum of from range L comma R. So what we are doing is we are first getting the sum that is lower and equal and lower than R, our right value. Then we are subtracting it from all the keys that are lower than L, that means the lower value. Now first we will calculate sum of all keys that is equal and lesser than R. For this I have written a pseudocode that will explain how we are getting this sum, and basically we will be using this function for every time we need to do any kind of query. Now first function sum of x, what it does, we take first a root node and then the upper bound. So here x is the upper bound. Then we'll first initialize that total sum will be 0 and current node will be a root node. Then this is a function that basically get the subtree sum, and it is already saved in our node as node dot as subtree sum, as we are using an augmented AVL tree. Now first we'll start a while node will be start this node, and for the first case we'll be checking if the current key is less than x. So if this is the first case, and if it is true, we basically add this to total sum and the current node dot key. But if if it satisfy this current key lesser than x, the key in the left subtree are smaller. So we also need to add all the keys that are all the node that are in the left subtree. So here we are doing this again, like total sum will be added with get subtree sum and with the current node dot left. Now there are some values that are there are still some values that are less than our key value x, but it might be lying in the right subtree, we don't know. So we need to check it for the surety. Now so we'll be setting the current node to current node dot right. So if it does not, if it is not less than if it doesn't meet our first case, then it must be the second case, where second case is the current key is greater than x. So that it means that its entire right subtree are greater than x, so we don't need to add anything, and we need to continue our search from the left subtree. So we are selecting that current node will be current node dot left, and we'll be returning the total sum. Now the traversal take only log of big O of log n time, and the aggregation of subtree sum takes only O of 1 time, as it is already pre-computed. And finally what we are doing is we are adding the range sum for the, as we know, the main equation of difference of prefix sum, that we first calculate the sum of right and sum of left. We need to remember that when we are sending the node key value, it must be in case of sum of low, it must be L minus 1, as we have seen in the difference of prefix sum. We need to understand that for the first time we already took this value, so when we are calculating the total range, we cannot take this again, so we need to subtract this. Now we'll be returning the sum or minus sum of L, as this is our main equation for the difference of prefix sum. Here we have written the main equation. Now as the final subtraction only take O of 1 time, so our main concern is traversing through all the node. This is the main time complexity that we need in our range sum query. We don't need to worry about calculating or doing anything else. So the range sum query will always be in O of log n time. Now for the follow-up question, how would my approach scale if each tree update must propagate feature for downstream ML models? So for this we need to think about two things. The total cost, what will be our total cost? The total cost will be the traversal cost plus the feature propagation cost. Now, as it is a self-balancing BST, so the traversal cost will always be big O of log n. Now we need to think about the feature propagation cost. Now, for the feature propagation cost, we assume that it is f. There will be two types of features. For the first feature, we have simple aggregable feature. I mean that can be computed in locally in constant time. So what, for example, I have taken the like count of nodes in subtree, min max key, standard deviation, small or fixed size feature vector. This type of feature calculation can be done in O of one type. So for this type of features, our total update cost will be big O of log n. It doesn't have any problem. But the main concern is if our feature is complex and non-aggregable. For example, we have a complex statistical distribution or deep embedding vector. For this, we assume that our cost is big O of s. So our total update cost will be big O of s log n. Now for this kind of complex scenario, we can scale this by doing asynchronous pipeline or streaming updates. So what is this asynchronous pipeline or streaming updates? So I have added a pseudocode to explain it. So for this, what we will do, we'll be update only the core of the AVL tree and record which nodes are affected with its ID or keys. Then we'll push those updates to background job queue or streaming system. We will have some Kafka or RedStream system, and this feature computation service consumes those updates and recomputes feature asynchronously. Now for this, what I have done is, suppose I have a tree, AVL tree, that every time any kind of insertion, deletion or any kind of update happens, it will publish this key value and our event. So here the event is insert and the key value, we are publishing it to the stream, and we have a asynchronous feature worker. What this worker do, this worker takes the feature update, what is the event and what is the key, then it update, then it calculate what will be a new feature, then again it update the feature store through via node key and features. So if we maintain this logic, the AVL tree can handle data access range queries and structure efficiently, and ML models get continuously updated features from a streaming pipeline. This actually offload our heavy ML feature computation to parallel background tasks and maintains the AVL tree time complexity of O of log n. So now for the question 2, the question is, suppose you must store and retrieve large model weight files distributed across a database. Explain how a B tree supports fast search and insert operation at scale. So follow-up question is, how does this apply to feature vector lookup in recommender system? So we need to use a B tree to retrieve the large weight files. So here how we can use the B tree. So basically a B tree is a self-balancing tree data structure that maintains a stored data and allows searches, sequential access, insertion and deletion in logarithmic time. So in a B tree, each node can contain multiple keys which lead to fewer levels in the tree. This process helps to faster data access. So unlike binary search tree, a B tree can have many children per node. This makes a B tree perfect for system where disk input output operation is a bottleneck. So in B tree, the node size is equal to the page size. Now a B tree node is not an arbitrary size. It is carefully designed so that its full contents, like all its keys, values and child pointers, occupy a space that is exactly equal to the disk space size. Now if the disk space size is 4 kilobyte, the B tree node is sized to be 4 kilobyte. Now this 4 kilobyte is a huge number because for storing a key value pointer, we will have at most t equal to a 200 around size. So the single input output operation loads the entire node into the memory, instantly giving the CPU access to almost 400 different possible paths to the next level. Now, as nodes are large, it can contain many number keys and a large number of pointers to its child nodes. In a large database system, multiple keys can hold multiple child pointers. Now, the multiple keys per node concept reduce the height of the tree. The height of the tree represents the number of disk input output per operation. As the height of the tree is in B tree is minimal, it is optimal to use this system in a large database, specifically storing the large model weight files. Now, in case we use B tree for storing the database indexes. It stores the key and the pointer that points to the distributed files, and the large binary files, model slices or tensor slices are stored across the distributed file system or cloud storage. Now, for this, I'll explain this with a simple flowchart. So what happened is we first create a B tree index on the targeted column, then we insert the data into the table, and this will update our B tree index with the new data. Next, we execute query and use the B tree index to find matching records and then return the query result. And now this happens in almost a constant time because we'll explain this in the insert operation. Now, B tree uses a self-balancing mechanism. If a node is full, it performs a node split operation where the median key is promoted to the parent node and the existing key are distributed between two new siblings. This mechanism ensures all the leaf node remains at the same depth. By keeping the height small, they guarantee the complexity of big O of log n in insert and search time. So what happens? We first start with the root node, then following the path, we reach the appropriate leaf node. Now, after when we reach the appropriate leaf node, we check if it's full or not. If it has space, then we insert the key value. Now, in keysar key, it represents the ID and the pointer value named weight pointer. Basically, this point to our main weight files. Now, if the leaf node is completely full, this node is divided into two new nodes, and the median key is promoted to the parent node. The two sibling nodes become the children of the new parent node. This is the most costly operation in the B tree, but as a node can only have at most 2 t-1 entries, this happens very occasionally. For this, I use this graph where I will be inserting some values. For example, in the second, when I insert the 60, now what happens here? As this node can only have 4 child, when I insert the 60, the median value 30 become the parent, and other value these two become the sibling of this value. Now, when I again enter other values like 70 and 80, it will be okay because it has reached its maximum value. Now, when I again insert 90, now what happens here? When I insert the 90, 60, this median value become the parent, and this become the sibling of other children. Now here only now I will be explaining the B tree search operation. So the B tree search is based on the many children per node concept. As the height is minimized, the search is much more faster. The search start at the node initiating the first disk input output operation to retrieve the entire nodes page from the distributed system. Now the system compares the target node with all the key values that are stored in the root node. This search is an memory search which is very fast. Now what is this memory search? So what happens here is that I first in the memory, the node is extracted and give it to the processor. Now processor is very fast to compute and compare these values. Now the main issue is the extracting the node from memory to processor. This is the actual time we need. But in our B tree, we in per node we can store many children. So when we extract a node, we can extract many keys and value, and the processor is fast enough to compare all the values and give a resultant node. Now the system compared the target node and all the key value that are stored in the root node. This search is in in-memory process, so it will be very fast. Now if the node found its targeted node the search is complete, then it retrieves the weight pointer that is linked with the targeted node. Now if it does not find the node, we can go to the child pointer into the next level. So this section usually takes 2 or 3 repetition, so the height of the B tree is very minimal. So I have written the pseudocode here. In this code I first initialize the B tree node, what a node can contain. So in a initialization, I check if it is a leaf node, then the tensor ID. Basically tensor ID is my key, and the weight pointer actually the value, the targeted weight value, and the child pointer, how many childs are containing. Now how the search works: first I give the function a root pointer node and ID. Now then the root pointer node is initialized into current node pointer. Now I start the while loop. Now in this while loop, first current node check the current node pointer. Basically it is in the disk page space. So if this function will give us the current node pointer. Now the in-memory search happens. In-memory search is basically occurs at the processor, where processor just checks the tensor ID and the target ID. If it matches, then successfully we return the current node weight pointer, and if it does not matches, we then prepare for the next level, where we check if it is a leaf node or it does not. If a leaf node, then we terminate the process, or otherwise we found the targeted node. Now this whole process always computed in a log of n time. Now for the B tree search process, the time we need is the number of IO operation and into the cost of IO plus total CPU time. Now for this, the IO operation is a logarithmic time, and here the B is the binary search vector, which means the number of child pointer that are connected with the node. Now what is this C actually the CPU time, which will be constant, so we don't need to worry about that thing. Now how does this apply to a feature vector lookup in recommender system? So we use B tree to find the user item vector based on its primary key. The B tree stores the index of the unique scalar ID of the user or item, and the value means the specific vector is stored in a database. This B tree index can locate the specific vector location and can perfectly retrieve the vector. So in a distributed vector database, B tree is used to manage the metadata, which is based on the specialized vector index. A feature vector are often partition the vector space into segments for parallelism. A B tree is used to index these segments. A query search is held in B tree. This B tree can identify the vector index file, then hands the vector search to specialized ANN algorithm. So ANN is much more efficient than B tree, because we use ANN to reduce the search space. Instead of comparing all the vectors, ANN selects a subsets of vectors to compare against the query vector. So what happens that B tree ANN vector calls the B tree to retrieve the index of the vector that it needs, and it happens very fast, because we know that B tree time complexity big O of log n. So ANN algorithm can very easily retrieve all the vector that it needs using the B tree, and we can complete our vector lookups recommender system very efficiently and faster. Now for the question 3, we need to outline an algorithm for finding a minimum spanning tree MST in a distributed system. Following up question is that in what real world ML scenario would you use MST? So for the answer, basically here we will be using a famous algorithm, the GHS algorithm, which is already built for the distributed system. For finding a minimum spanning tree in a distributed, we need to construct such a network where nodes are operated as independent units and can communicate with their immediate neighbors. We will be using GHS algorithm. This algorithm is a synchronous, and here every node proceeds synchronously in rounds. So what is this GHS algorithm? So GHS algorithm basically works in level by level. So initially we will be having a level 0. So in level, the algorithm operates in such a level-wise manner that it collect all the spanning tree that we call spanning forest. Now every component at each level has a leader, and the spanning tree is identified by that leader. In level 0, this level consists of all the nodes and no edges. Each node is a spanning tree, and for n nodes we will have n spanning tree. Now at this stage, every node only knows the total number of nodes and the incident edges to it and the unique ID of the leader of that spanning tree. Now for visualization, I'll be I saw this. So this is how a level 0 node look like. Here every node is their own spanning tree, and they just know the number of nodes there, incident edges there, and the unique ID. Now we have to merge these two components. Now what are this component mean? So component means basically this connected tree that we have seen here. We can see the two components. Each component can have many nodes, but they will be interconnected. But we need, our main goal is to connect these two component. Now we need for this here no node knows which are the edges that go out of that component. So for this, each node within the component send a search message using BFS to get the minimum weight outgoing edge. What we in short form we called it MWOE. After each node receives this search message, it searches for an outgoing edge that is going out of that component. Out of all the edges, it selects with only the minimum weight. Here I show you that if there are some edges that are connecting different component. Now the leader choose the lowest MWOE. MWOE, upon receiving the search message, every node needs sends a test message to its neighbor. Now each neighbor responds with the leader unique ID of its component. Then it compares with its own unique ID, and if the leader ID matches, they become the part of the same component. Otherwise they are not the part of the same component, they are different component. This is how a component knows that exact edge is connecting our component to other component. As every node knows of one outgoing edge that connects itself and the node to another component, it sends this message and node to the leader of the component. Out of all the minimum edges that leader receives, it evaluates the global minima and then becomes the edge that is MWOE of the component. Now for merging, the leader of the component talks with the node of the other component that was selected via the MWOE. It marks the edge to be in the new tree, where the leader of this merged component will be the node with larger unique ID of the two connected over MWE. This info get broadcasted across the components, so all component know that this is the leader and I am the part of this component. Now this whole process is done in level by level manner. Initially in a level 0, every node is a component itself. Then two level to 0 component merges and form a level 1 component. Also if one level 0 and one level 1 component merges, it creates a level 1 component. This process continues and level k nodes keep on merging and forming higher levels. In this way it can avoid merging conflict. So for this I'll be showing here. So in level 0, every node knows only there are this amount of node, but they are not connected. But in level 1, two node connects, level 0 node connects and make a level 1 component, as you can see here. Also if a level 0 and level 1 both merges, it will also be called the level 1 component. Now how do we know that our process is complete? So for this, what we do, after some number of levels, the spanning forest will contain just one tree containing all the nodes. Each node will know the edge part of the spanning tree. When the algorithm will try to find MWE, it would not find any, because there's no MWE edge. The leader will know about this because it would get empty responses from peripherals node suggesting that the algorithm has completed. Now for this, what will be the time complexity? As we know, at each level there are at least 2 to the power k nodes, as the components are merged by levels. 2 levels are merged at log of n. Each level take O of n times. Here time complexity is O of n log n. Now if we add this with the communication complexity of O of e, our whole complexity will stand at big O of n plus e into log n. So for the follow-up question, in what real-world ML scenario would you use MST? Now, MST is used in ML as a pre-processing step to understand data structure or as a component within a larger algorithm. The most useful tasks are clustering, anomaly detection, and feature selection. Now, I'll be discussing the cluster analysis first. So, what happened in cluster analysis? That MST use hierarchical clustering and density-based clustering, as this algorithm can identify cluster of various shapes and sizes. So, in hierarchical clustering, a device approach where an MST is constructed from a dataset and then cluster are formed by progressively removing the edges with the largest weight from the tree. It first calculate the distance matrix of the data points, use an algorithm like Prim's or Kruskal's to construct a MST, which connects all the points with the minimum possible total edge weight. This process of removing largest weight edge and splitting cluster is repeated until each data point is in its own cluster, creating a hierarchical clusters. Now, for density-based clustering, it involves constructing a MST on a dataset and then removing the edges with high weight. The algorithm uses Prim's and Kruskal's to build the MST. The weight are the distance between two edges. After constructing the MST, the algorithm then removes the edges with the high weight, the remaining connected component of the graph after the cuts are resulting cluster. So here what happens that if we found an outlier, it must be have a high weightage value, because it is very far from the main leader or our cluster. So we can easily remove that outlier and make a nice shaped cluster. Also, we use MST in anomaly detection and outlier detection. Here we use the local MST algorithm that uses MSTs for unsupervised anomaly detection by identifying points that are poorly connected to their local neighborhood. There are two stages of detection process. Global anomaly detection. Here a global MST is built and it removes the largest edges to isolate anomalous clusters. Now, local point-wise anomaly detection. In this use the local MST properties to detect individual anomalies within normal cluster. So there is a paper named Unsupervised Anomaly Detection based on minimum spanning tree approximated distance measure and its application to hydropower turbine. This paper shows that it has successfully applied to hydropower turbine monitoring system with over 200 sensors attributes, demonstrating remarkable detection capabilities for maintenance prediction. We also will be in ML scenario, feature selection MST is used, because if you have a data set that contains multi-dimensional data, especially in time series data set, there is a lot of redundancy in this data streams, and good accuracy can be achieved with a small number of features. Here features mean the dimensions. In this scenario, MST can identify the optimal subset of P features that minimizes the MST length of the resulting graph. This approach is a good combination of hierarchical clustering with feature selection. In feature selection, we don't need all the features in our data. We need to choose which features are the most important for us to use, and MST helps us here to choose the optimal feature for our dataset. So for the question 4, the question is, for a tree or graph based feature index in a memory constrained environment, compare slab allocation versus garbage collection as memory management strategies. The follow up question is, which option better supports predictable latency for online serving in ML system? Now, for the slab allocation, it is a mechanism for efficient memory allocation of objects. In the kernel, a slab allocator divides objects into graph called cache. Each cache stores different objects. These caches are divided into slabs. A slab contains many contiguous pages that contains the number of objects of the data structure that is being cached. Now, in the flowchart, we can see a cache that is connected with three different type of slabs. Now these slabs have a significant meaning. The slab full means all the nodes are fulfilled with objects. The slab partial means some of the blocks are used, and slab free means none of the blocks are used. So it basically have pages, and pages are connected with different type of object. Now this object mainly indicates the size of the object. So when if a object has 4 kilobyte of memory and if another object takes 16 kilobyte of memory, they will be divided into two subsection. Now the main principle of slab allocator is cache commonly used objects so that the system does not waste time allocating or initializing and destroying objects. So the allocation and deallocation happens in constant time. In slab allocator, a schema named slab coloring is used, which utilizes the leftover space in a page to increase cache utilization. This helps the same field in object from different slabs to map to different cache line, which helps to avoid cache thrashing. In case of a tree or graph based feature index, slab allocator uses a mechanism where it releases object after use but then cached without immediately destroying them. This allows the allocation to be ready to be reused by an object of the same type. Now in cache of tree or graph structure, slab allocation provide a superior memory locality, as in tree traversal, or a system needs to access many related nodes of same size which can be stored in the same slab. This improves cache performance and the locality advantage for a memory constrained environment. Slab allocation provide a predictable memory uses, as slab allocators initially try to use the partial slab first and then the empty slab. So in this specific scenario, slab allocation is a superior choice. So in this picture we can see that there are different sizes of object and each size object has three kind of slab. So when a 256 bytes of object come, it first directly go to this and go to the partial slab, as the partial slab is the main priority. Next it will fulfill the free slabs. So in what is a garbage collection? So garbage collection automatically identifies the memory that are no longer usable in a program and reclaims the memory by allocating the memory to a pool of memory location. In a tree or graph like feature index, it will need to free the nodes that has been deleted or it is not being in use. So in this picture I have taken from the GC process summary. This is basically the Java virtual machines garbage collector. Now how this work, I will explain it in a word like this. It shows how newly allocated objects are first placed in the Eden space and they are here and they survive subsequent GC cycle, that means the garbage collection cycle. They are moved to survivor space. Objects that survive long enough eventually get promoted to tenured or old generation space. Now this number basically is the age, indicates the age. Every time a GC cycle occur, if the object survive, the age will be increment by 1. Now we'll discuss how garbage collection works in tree-based feature index. So although the garbage collection is a faster and automatic way of dealing with frequent allocation of a short-lived object, but the main issue concerns with memory management. For a garbage collector to operate properly, it requires 2 to 4x more memory than manual memory management, as they used both for a living object and the garbage object. Also, garbage collection deals with the short-lived objects more efficiently, but in a tree graph index typically contain long-lived structural data that doesn't benefit from garbage collection. So in a word we can say that in our case, like in the memory constrained environment, between slab allocation and garbage collection, slab allocation is the definitive choice. Now comes the follow-up question. The question is, which option better supports predictable latency for online serving ML system? Now between the slab allocation and garbage collection, clearly slab allocation gives better support in predictable latency for online serving in ML system. I will discuss some point why slab allocation is better. The first point is that constant time allocation. So slab allocation delivers allocation and deallocation operation in big O of one time. So it's a constant time. This makes the response time highly predictable and which is crucial for online serving ML system. And what this basically means that an object can easily being allocated or deleted in constant time. In case of memory bandwidth in a machine learning system, for generating the first token is typically a computed bounded system, while subsequent decoding, I mean the next token will be generated by a memory bound operation. Here slab allocation can efficiently utilizes the memory through caching. In case of event handling, unlike garbage collection, slab allocation doesn't require to pause the entire system, as we have seen that in garbage collection they are named that GC cycle, which basically try to check out which are the living objects. So when this happens, the application is being paused. So but in the case of slab allocation, the entire system can easily the entire system doesn't need to get paused, and it can reclaim its memory. In ML serving system, this is extremely crucial, as this leads to request timeout and cascade failure for the of the whole system. Now, in case of consistency in memory access, in slab allocation, memory access patterns are done via cache, as the segregated storage approach ensured that related index nodes are co-located in memory, improving cache hit rates and reducing memory access latency variance. So, what are the disadvantages of garbage collection? So the main disadvantage is that each time a GC cycle occurs, the application needs to pause for a moment to allocate and reallocate the memory and objects. Now this unpredictable time causes a non-deterministic latency, especially in our case in online serving ML system, while low latency is very crucial. So we can easily say that for an online serving ML system that demands constant and predictable latency, slab allocation is the most suitable choice. Thank you.